Hey, hi. Good afternoon, everyone. Okay. People are joining in slowly. Okay. I see a few more people joined. All right.
20.
Can you hear me, Ashok? Yeah, I've just shared a poll. Please, everyone, comment if you're able to hear me and see the screen. Okay, great. All right. So we're just waiting for a few more people to join in. We would be probably ending the session tomorrow. Uh, there are a few people who are not able to hear me, is it? Okay, you're able to hear me. Okay, just for fun, let me take the poll. We are creating a poll. What is the thumb rule of correlation coefficient to interpret relation between two variables as strong? What is the standard value to declare that a variable is okay? Just try and answer this question. What is the rule of thumb for correlation coefficient? What is the standard? Very good. Yes. It's greater than 0.85. Wonderful. Hmm. 0.5. Okay. That's strange. Why 0.5? Yesterday we discussed that the thumb rule says that the modulus of R should be greater than 0.85 for us to declare that the relationship is a strong relationship. Right? So it should be greater than 0.85. Anything which is less than 0.5 we generally consider as weak. Right. So it's 0.85 friends. All right. So let me talk about yesterday's session, what all things we have covered yesterday. So we started understanding the relationship between two variables using the base equation y is equals to f of x. And we learned that there are two ways to define this function. One is the predefined equations. And the other one is the black box. We will try to look into black box tomorrow. Okay. Now in the predefined equations, that means you will be able to explain the value that you are going to get. You can easily explain the relationship between y and x using the function that we are obtaining here. And these predefined equations, there are n number of different equations. We will try to fit in those equations to the given data and see whether the equation can actually explain the relationship or not. That means if I substitute x into the equation, then I should get y. But this y may be deviated from the original value. The original value is y. So the difference between these two is the error in your prediction. Right? The error that we are getting in our prediction. Lesser this error, better the model. Lesser the error, better the model. Remember that. Now we are trying to see various models, various equations, which can actually bring this error down. That's what we try to learn. Now, when you're trying to predict this y, in your historical data, you already know. What is the data, right? You already know in the history. So if you already know your data, we will be able to tell whether the data is a numeric data or a non-numeric data. In yesterday's session, we discussed about linear regression model. Now, these regression techniques are applied when the variable of your interest that you're trying to predict is numeric in nature. And we applied linear regression because when you talk about numeric, the data could be continuous or it could be discrete as well. The data could be continuous or discrete, right? Numeric data. The non-numeric data, that is your categorical data, which we basically call as discrete data. It will always be discrete, okay? Non-numeric will always be discrete. For these kind of data that you have to predict, we generally go with classification models. These are classification models, or we call them as classifiers. So if you are trying to predict a numeric value, then we call that as regression. Okay, let me erase this linear. We call it as regression. And in the regression further, if your data is continuous, we'll apply linear regression. If it is discrete, then again, it has multiple options in discrete. Discrete, it could be binary, it would be greater than category, 2 category, or it could be a count data. Binary, then you'll apply logistic regression. Right? If it is greater than 2 categorical nature, then again it is classified as 2 types, nominal, ordinal. And for count data, we have count models. And here we have different types again. Poisson, negative binomial, zero inflated models, right? All those things. Different models will come into the picture. We have seen this as part of yesterday's session. We see how this equation that we are very well versed with from our childhood days, we have learned about this, y is equals to mx plus c. This equation is used to try and find the relation between y and x. So mathematically, if I can look at the relationship between y and x as being consistent, right? If the relationship is consistent, then we can use this equation. Consistent, and of course, it has to be linear. If this is the kind of relationship that we are getting between x and y, then we define this equation. And using this equation, we'll try to predict y value given the x. And statistically, we write this as beta naught plus beta 1 x. Now we'll extend this equation to multi-factor scenario, multiple variable scenario. So if you have various different factors influencing y, then we keep adding these variables. We are trying to capture the effect of the variable on y using this equation. This is only when one variable is there. This is when you have multiple variables. Right? Now, we also have logistic regression, as I said. Now, logistic regression is used when your output variable is binary in nature. Okay? And we also have to fine-tune these models, regression models. And in order to fine-tune them, we'll apply something called as regularization, or we also call it as L1 norm and L2 norm, normalization or regularization techniques. And here, L1 is lasso. We call it as lasso regression, also known as shrinkage technique. And L2 is called as ridge regression. Now, these two techniques are used for fine-tuning your model. In simple terms, we'll apply this to make sure that the accuracy is increased in the right way. tuning parameters or regularization parameters is what you can call it. So in both these models, right, the simple logic which is applied is try and remove those variables which are not putting effect on y much. In lasso, it will make the coefficient as 0 so that the effect of the variable is completely removed. Unrich, the value of coefficient is made close to 0. It will not be 0, but it will be made close to 0. By applying this, of course, regularization techniques, it's again a detailed discussion that we have to have if you need to understand these cases. Which is, of course, covered. All these are in detail covered in our flagship program, which spans till all the concepts will be covered in 184 hours together. So in which we'll cover cloud, we'll cover SQL, we'll cover big data, we'll cover all these different regression models and all that. So that's about regression. Okay, in short. Now today we are trying to understand classification. Classification models. So when I say classification model, the output variable that you're trying to predict should be non-numeric. Okay, it should be non-numeric. So that non-numeric case is very easily resolved using this one of the simplest machine learning algorithm, which is called as KNN. The concept is very, very straightforward, very simple logic is applied, but the applications are immense. It can be applied in a lot of cases. So let us try and understand what exactly KNN is and what exactly is machine learning is here. Let's say we have handwritten numbers. Okay, I am collecting the data from all the people. Let's say in the university, I have all the students, professor, visitors, everybody, the staff. I will ask them to write numbers from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Okay, 0 to 9, I'm writing the numbers. I'm asking everyone to write the numbers. Now, each and every person would have a different handwriting, right? You can see each one has different handwriting. None of them will have same handwriting, right? Now, I want to pass this data to my computer, to my system or machine, and I'm asking my computer or machine or the system to identify a new letter. Somebody is writing this new number or letter, right? Handwritten, mind you. I would say this is handwritten. Specifically, you have to write it handwritten. If it is handwritten, then your system should be able to identify what that number is. For example, few people will have right handwriting like mine. My handwriting is antique. Nobody can come closer to my handwriting, right? So that is one USP I have. Now let's say I'm writing a check, right? I have to pay money to you, so I'm giving it in a check form. Right. What is this number? Can anyone tell? I also don't know what did I write. Can anyone guess what is this number? I'm writing this on a check. Handwritten. Nobody is dare to guessing, is it? Yeah, anyone, what is this number? You can put a message in the chat window. I'm looking at chat messages. Okay, 53585. 3, 3. Okay, yes, somebody's saying yes. Okay, then okay. So 5, 3, 3, 8, 3. This is what I was writing. We humans cannot identify if I write something like this, handwriting. Weird handwriting, right? Of course, that's the reason why you have letters. You have to write the same number in letters as well, right? In the checkbook. But let's say we have now developed an ATM machine. Few banks have already done this. The ATM machine that we are talking about is only dispensing the cash. You type in everything and it gives you the cash. But what if I want to encash this check, right? So you have to go to the bank, stand in the line, get the code, get the, what do you call, the coupon number, your coupon number. For your turn, you have to get a coupon, and you stand token, or you call it as token, right? You stand in the line, and your turn comes. You pass this check. The person, the teller who is there in the bank, he is trying to figure out what that number is. He'll look into the letters. He'll try to figure it out. Then he will look at the signature. He sends that check to his peer just to make sure that there is cross-validated, cross-check on whatever he found is correct or not. And once he gets the approval from his peer, then he is going to dispense the cash, give the cash. So there is a lot of effort which is going on here, right? Manually. And as a customer, you have to wait for all this time. You're just waiting there to get your money back. I mean, get your money. Right? So how about trying to get the money directly by, let's say, check. We have check given. Okay. You pass this check to the ATM machine. Now ATM machine is looking at these numbers, and then it is figuring it out on what is the number. Of course, it also has to read the letters, characters, and it shows on the screen on what is the confirmation. And if you feel that yes, that's the right number, then it probably, right, provides you the cash, directly gives you the cash. But remember, this machine has to understand the number. That is the tricky point. How does your computer learn about these numbers? That's something you have to think about. We are talking about machine learning, right? Machine learning. This is what learning is all about. So we collected the data here, right? For all the customers, all the visitors, all the students, whoever is coming to the university, we asked everybody to write the numbers handwritten. And we feed this information to the computer. How I'm passing this? I'm saying, hey, this is class 1. This is class 3. This is class 2. This is class 4. You're labeling them, right? And you're saying, hey, computer, hey, machine, if you see something like this, treat that as 0. If you're seeing something like this, treat that as 9. So on and so forth. You are training your computer. Your computer is learning. Right? Under the supervision of these labels, it is trying to figure out the pattern. Yeah? Now, if you see this, if you are passing this number to your machine, then it has to quickly look into all these numbers and see what is it similar to. What is this number resembling, right? Closest resemblance is where in all these classes, what is the closest resembling number? So it finds this. But this is belonging to class 4, right? Hence, we declare that this also should belong to class 4 or category 4. Very simple theorem, right? And very simple logic. Try to map, see which one is closest resemblance. And that closest resemblance will be applied here. Right? Now, I'll show you one interesting video, friends. This is what machine learning is all about, okay? We are taking it a step ahead and taking it to, I should say, AI. Let me see if I have that video, deep learning. Yep. Observe the screen very carefully. We're talking about machine learning here. Okay, are you able to see the screen? Please confirm, are you able to see the screen, friends? The video? Yeah, sorry about that glitch. Are you able to see the screen now? Can you please confirm? Yeah, friends? Okay, wonderful. Yeah. So this is Google's DeepMind algorithm, which is basically used to execute a game, video game. The game is Atari Breakout. Our algorithm is trying to learn the Breakout example or the video game, and it is trying to become better and better there. Machine is learning, right? So that's the example here. Now we need to understand that the algorithm, the agent that we are talking about here, is given only one question or one point, which basically is ordered to maximize the score. So it has to score maximum marks. That's the logic. That's all you're asking your machine to do. And then your algorithm is running. So no input given, friends. We have not shared any input. No domain knowledge is involved in this particular training. So see what happens when the game starts, right? In the initial 10 minutes. So imagine that you have a 5-year-old kid, okay? Or 4-year-old kid, and you're giving him a video game to play. You're giving a video game to that kid. You're not saying anything. You just handed over the video game to them. Of course, nowadays generation says, hey, this is not the video game that I want. I want another video game. Right? So they are very well informed about all these gadgets. But let's assume that you're giving a video game and this kid starts playing. The initial 10 minutes, look at what happens to the algorithm here. It's just like behaving like a human. Observe. It is trying to figure out the game. Slowly it is trying to understand, okay, I should make sure that the ball does not fall. I have to move the bar in such a way that it makes sure that the ball is bounced back and I get scores. So it's trying to figure out. Now that is in the initial 10 minutes. Kid is also same, right? He'll be very rusty when he starts playing with the video game. But as and how he practices, as and how he starts playing, his memory is trying to, right, enhance on the learnings. Same way here, the algorithm is constantly learning, and now it has been 120 minutes of training. Look at that. See, it is not allowing the ball to fall, but that is not it. That's not it. This is machine learning. Now, on top of that, imagine we have to go for AI, right? We're talking about artificial intelligence. You're automating the process. So see what it does. So after 240 minutes of training, the agent is trying to find a shortcut to improve the score. It's performing better than humans now. It's figured out that sending the ball above by creating a tunnel would basically give us better results. So this is our machine learning, right? This is Google's algorithm for you. It's called as deep learning, deep mind. So we are trying to do the same thing here. We are passing as much as data possible, saying, hey, if you see this kind of a letter, then treat that as 3, this as 1, this as 5, right? More the data, better the training, better the learning. And it tries to figure out what is the closest resemblance. And based on that, it is saying that class, it's identifying the class category. Now, to understand this, I'll take another example here. Let's say I have, assume 2 different parameters. I'm taking 2 values. One value I'm plotting on x-axis, the other value I'm plotting on y-axis, x and y. So x-axis, let's say, is assume age. On x-axis, we are plotting age. And y-axis, we are talking about, let's say, body temperature. And we have 2 categories, pink class and blue class, right? Blue and pink classes. Let's assume that this is COVID-19 positive, COVID-19 negative. Now, given this information about your historic information, your past patient's data, when a new patient is given to you, you have to identify, you have to classify whether the patient has COVID-19 or not. So you have to train the machine to identify the pattern hidden in the data. Now, what we do is, mathematically, in order to identify that, we take this data. This is your new data, new customer, and we measure the distances. We measure the distances like this to all the existing historical data. So I will take this new data, new patient, and I'm trying to see to whom this new patient is closely resembling to with respect to these 2 parameters that we have plotted here. Using those 2 parameters, which customer or which patient is this new patient similar to, right? Distance is what we measure here. And how many of you remember the distance formula? Okay, I don't want to give hints. What is the distance formula called as? I wish I had filling the blanks option here. What do we use? Or let me ask you this way. Let's say I have x-axis, y-axis values, and I have data, x, y. So all these x values I'm plotting here, all the y values I'm plotting here. And to map to one record, we create a dot, we represent that dot, which is nothing but x1, on y-axis it is y1. So let's say I have another dot. This is x2, this is y2. Now I want to find out the distance between x, this, let's say A and B. Record A and record B. What distance between A and B? If you have x1, y1, x2, y2, the distance between the data points is measured using this formula, square root of y1 minus y2 whole square plus x1 minus x2 whole square. Remember this equation, square root of x1 minus x2 whole square plus y1 minus y2 whole square. This is called as distance measure. And this distance measure has a name, which is Euclidean distance. We call it as Euclidean distance. Right? So we measure the distance from this data to this data. Okay, what happened again? Let me check. Looks like some network issue. All right, yeah. So we are measuring the distance between x and y. This is A, this is B as you. Similarly, AB, 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 AB. We measure the distances and we'll mark that distance here. Distance 1, let's say this is record 1, this is record 2, record 3, so on and so forth. So I'll measure the distances like this. Among all the distances that we have, we will pick the shortest distance. We'll take the shortest distance here. Yep, shortest distance. And that shortest distance, let's say assume is this pink class in this particular diagram. So because it is closer, the new record is closer to the pink class, we assign the new record to pink class. Right? Now, this technique that we are applying is looking at one shortest distance. Hence, we call it as 1NN. We call it as one nearest neighbor. But again, why should I take only one? It could be an exceptional case, or it could be just by chance this record is closer to this record. By chance it might be there, right? So we might have different, we have to try with different K values. And that is what we call it as KNN method now. So this K has to be altered. We keep trying with different K values. So when I take K equal to 2, then I'm going to measure the two shortest distances. So it will be two shortest distances here. This is 1, this is 2. Right? Two shortest distances. All right? Now, the question here is, there is an ambiguity. There's some ambiguity here. One is blue class, the other one is pink class. We are taking two shortest distances, but there is an ambiguity because one is pink, one is blue. So in such cases, we go with the closest one among the two. Because this new data is close to pink, we assign it to the pink class. But let's say I have another scenario like this. I'm taking now odd number. So here, the new data that we have is having two blue classes and one pink class. Because of this majority, we assign the new class to blue class. Right? So on and so forth, we keep on trying with different k values, and we'll try to find out which k value is giving us the best result. Right? Best result means your predicted value and actual value should be same. So we keep trying with different k values. This is your k nearest neighbor classifier. If you change k to a higher number, you get more number of values. Right? So we keep trying to play around with the k value. But when do we stop is the question. So here what we do is we take the historical data and we partition it, split it. We take majority of the data as training data and the minority of the data as test data. Randomly we split. And then we use training data here to identify whether the k is, whatever the k that we are trying to figure out, right, is giving us the appropriate values or not. Yeah. So here we are saying take the training data and train it. That means you build a KNN method. Now, because you already know the data, you're adjusting the k value to find the best k value. Right? So that means, let's say you have multiple variables. You have one y. You know this y already, historical data. So we develop this algorithm in such a way that we try with different k values, wherein substituting of that k for the distances will always give us the right information. It is predicting correctly. But that model may not work when you have new data. May or may not. To make sure that the model is working, right, as expected or at an ideal accuracy, then we look into the test data. This test data will have both input and output. Test data will have both input and output. Of course, train will also have, but you're using this training data for finding out the best k value. Now, from the test data, what we do is we take the factors, input factors, and arrange the data like this. Right? And then we apply different k value or whatever the k value which worked for training data. We use that k value into this scenario, into this data. You'll take only test data, arrange the test data here. So let's say, assume I have 100 records. So I 80, 20. This would become training data. This would become test data, right? So these dots that you are seeing are training data, assume. So I will take k is equals to 1 first. First record of the test data is taken, right? Assume this is your first record in the test data. We measure the distances, we find the closest distance. And observe what is the k value, what is the outcome if you choose k value as 1? Let's say it says pink class. In the test data, you have x and y, both are none. But we are trying to apply logic to predict y. So if I say x equal to 1, k equal to 1, then what is the y value that I'm getting here? Right? Let's say actually it is pink, but you're predicting it as blue. Your model has predicted it as blue. Then that means it's wrong prediction, right? It's a wrong prediction. But if it is saying pink, then yes, you are correct. So we will verify it on the test data for all the 20 records that we have here. And we'll measure the accuracy. Accuracy basically saying how well is this model predicting on new data, accuracy. So if the value is P and if you predicted it as P, then it is a correct value. Your prediction is correct, right? But if your value is pink class, but you predicted as blue class, then in that case, it is a wrong prediction, right? So this way we'll measure the number of times the model has correctly predicted on this particular 20 records data, right? And those predictions are stored for our analysis purpose. So always remember, when you are measuring the distances, it will go with majority first. And then it goes with the shortest. Majority first and then shortest. And we can see here, majority is there. Pink is 3 times. And it is close. Okay, this is ambiguity here. I have even number. So no, 7 members are there, right? Okay, odd number only. So I have 3 pink class and 3 pink class and 4 my bad, 4 pink classes and 3 blue classes. It's like a tongue twister now. Blue class, pink class, blue class. Because it has less number, we are assigning this to new number, which is shortest value, pink class. Right? So this is how we generate the classifier models. The algorithm that we are trying to develop here should basically give us an ideal k value. So choosing the right k is more important, right? You're saying that, hey, accuracy is must. Fine. But that accuracy is working only on training data. Not good, right? It should work in generic cases. It should not work for one sample. So we try to come up with that particular value which is higher and which is similar between both these scenarios. Validation dataset and test dataset, both should be similar. So at what value of k we get it? That's what we have to figure out. That's what we have to find. And this is your KNN algorithm. So in order to understand this, I'll have another short example, very small toy example. So this is your ingredient data. And it has parameters x1, x2, and y. Right? Now, given these factors, sweetness and crunchiness, which are measured on scale, we should be able to identify if there is any new ingredient coming into picture as one of these food types. There are 3 levels. right? There are 3 levels, x1 and x2. These x1 and x2, we have to identify one of the food type out of these 3 levels: fruit, protein, and vegetable, right? But in order to do that, of course, I need to look into the spread of the data. I need to look into get the new ingredient as well. So when I arrange the data like this, it looks something like this. Rather than dot, we give the complete names. It looks like this. And when I try to find out the similarities between, then you can see here, we can form clusters, groups in the data. All the fruits generally have high food sweetness, right? Whereas vegetables, they have high crunchiness, right? And both of them are down, both of them are not high. Then we have protein, which is this one, which does not have good sweetness and which does not have good crunchiness. Yeah. So given this data, now if I bring in a new ingredient, let's ask this question, okay? Let me ask a question before proceeding. Okay, let me take a question. Yeah. Please answer this. What do you think? Is vegetable a fruit or a protein or a vegetable? Fruit, protein, or vegetable? What do you think? Tomato. Okay. A lot of people are saying it is a vegetable. 6633. I think not everyone is responding. Please respond, guys. It's just for fun. Somebody is thinking, a few members are thinking that it is a fruit. No, it is not a fruit. Sorry, it is not a fruit or a vegetable. I mean, that's not a question that we need to solve. Okay, somebody is saying protein. How can tomato be a protein, guys? It's either fruit or vegetable, right? Yeah. So if you ask me, I cannot directly tell whether it is a fruit or a vegetable. We don't have any formal definition for tomato, right? Though we consume it as vegetable, it also has all the characteristics that are required for a fruit. Yeah. So let us now try and identify whether tomato belongs to fruit or protein or vegetable. To which class should we assign this new ingredient? So here we will try to do distance, Euclidean distance calculation to identify the distances. This is the formula. If you have multivariate data, this is the formula. So let us try and do, this is the data 6 and 4, right? So let me go back to that data set 6 and 4. So I'm saying tomato, 6 sweetness and 4 crunchiness. And we have to figure out what is this particular data. Right, now, we have to create the distances. We have to measure the distances like this, existing with all the values. So I'm going to say tomato to apple, TA. So square root of 6 minus 10 whole square plus 4 minus 9 whole square. So this is 4 square 16, this is 5 square 25. Square root of 41, which is close to 5.4. I'm well versed with the data, don't worry. That's the answer, 5.4. This is the distance between tomato and apple. Now let's say I'm looking at probably pecan. So yeah, let's do this. 6, 4, right? So tomato to pecan. 6 minus 1 whole square plus 4 minus 4 whole square. $25? 5. Square root of 5 square, right? You're getting 5. So here you have 5.4 distance, here you have 5 distance, so on and so forth. We measure the distances, and then based on that, we take a call. Whichever ingredient the tomato is closest to, we pick that particular data as our closest data. Right? That would be our class. So you might want to try out, friends. This is the data. You might want to manually try and experiment on this. So you choose k equal to 1, which will basically give us the shortest distance. The value which is giving us the shortest value. Right? That is chosen here. If I say k equal to 2, right, then it will look at 2 shortest distances. Not 1, but 2 shortest distances. If I say k equal to 3, then you'll have 3 shortest distances. Right? And among these things, we first go with majority, right? And then shortest distance. Right. So this is how we train the KNN and find the appropriate K for our prediction purposes. Right. Any question? Yeah, any questions in KNN? If not, then we will look into the Python code. Now, as I said, the logic is very simple. We measure the distances and we take the shortest value. Right? But let me show you the application here. It's a data set where it's a health related data set, health, life sciences, healthcare, WBCD, which is basically talking about benign and malignant data. So let me load the data set and then I'll show you. Yesterday, we have learned about the libraries. So I'm importing 2 libraries which are mandatory for us to work with. One is Pandas. It's a data manipulation library. And the other one is NumPy, which is basically calculating the arithmetic operations. Pandas and NumPy. Now, once I've imported the data, I'm loading the data set. Right, so this is my data set. Yeah. Right. Now on this data set, if you observe, I have 32 columns and 569 rows. The first column is a random ID, employee ID, right? We don't require it for our analysis. You can completely ignore it. And the next value is benign and malignant. The diagnosis column that we are seeing is benign or malignant. Now, if you want to have the full name for benign and malignant, we can do this. Yep. So benign, WBCD diagnosis is benign. So wherever it is B, mark it as benign in the data set. WBCD underscore or in square brackets, you're calling it as diagnosis, right? So diagnosis column will update it with this benign value. So you can check now WBCD. Yeah, if you see here, we executed and we got the full names here. Right? We have executed the dates 2 lines to get full names assigned. Even if you don't have full names, then you just execute it and create the new names. Right? Short forms are not used basically. Next, I'm ignoring that first value. Yeah, I'm ignoring the first value or first field. How am I saying I've ignored the first field? If you see here, this WBCD is the dataset name, right? And in this WBCD, we are using the index location. I location means index, and we are representing rows, column format, rows, comma, columns. So if you observe here, I'm first saying row, there's nothing resembling, just colon are there. That means it is a row representation. And we have column. Right? This is the column data. And index always starts from 0. In Python, remember, index starts from 0. You can see here. Index is starting from 0. Yeah. Got it? So we are importing the data and excluding the value which is non-numeric in our data set, which is non-numeric, execute that data. Benign and malignant, that's not required, right? So we ignored it. Then the data that we have captured here is not normalized. It has different values, right? Different diagnosis values and different set of values here. So range is changing. And ultimately we are measuring distances in KNN, right? So if I have to make sure that the distance value is not getting affected by the magnitude of that particular value, if magnitude, right, is alone getting altered, not the actual value, then we do that using this normalization. So we are bringing the scale indifference here to same level. For example, let's say describe. Okay, let me use describe function here. I'll say WBCD dot describe. Count is same, minimum is varying, maximum is varying. Minimum has a different value, maximum is a different value for each and every column. That means the range of values is different. If you observe here, the maximum is 39, isn't it? And minimum is 4 point. Here, there's 0.00018. Here you have 0.06, right? Now on this particular data, if I can transform this data to same level, scale level, then it would be appropriate for us to measure the distances. See, ultimately you're doing this, right? If let's say it is only 2 digits and here you have 4 digits or 5 digits, what happened to the error calculation? Increasing, right? So I don't want this scale indifference. In order to do normalization, we use this function, custom function. You can give any name to that custom function. It is not restricted that you have to give only that name. It can take any values, but let me execute it and show you. Okay, just pass the data here. So you define the function here. What it needs to do when the data is passed is also given here, right? And we have to pass this normalize function to numeric values of original data, WBCD. 1 colon, because the first value is anyways diagnosis. There's no point in, right, conducting the security, or I should say, how can you combine? I mean, how can you measure the maximum and minimum range? We cannot calculate max or minimum on non-numeric data, right? Hence, we do not apply that normalization function on this. Whereas for the numeric values, I can apply this, right? So let us apply and see what happens. Normalize function. If you observe the function, it is trying to change the scale by applying this formula. But what is that formula? The formula is not defined, is it? Why it is not defined? I have not executed this. Okay, I have not executed this. Yeah, look at this. If you observe here carefully, the minimum is same and maximum is same. That means the range of the data will remain same always when you apply this function. So this is x minus x of minimum by x of max minus x of minimum. Now what happens, you apply this formula onto your data is, it is going to bring the scale of all the values to lie between 0 to 1. So I have an x variable, I'll say 1, 2, 3, 4, 5, 10. So I have multiple values. I want to normalize this data. So in order to normalize, we apply this formula, right? What is minimum here? 1. What is maximum? 10. So we apply this. X is the first value. 1 minus minimum 1 by 10. So this is 0. Right? Then we apply the same formula to 2. Now what happens? 2 minus 1 by 10. So this becomes 0. This becomes 2 by 10. Sorry, 1 by 10, my bad. Now we are applying this third one. 3 minus 1 by 10, 2 by 10, 4 by 10. 5 by 10 is 1 by 2 and 10 by 10 is 1. So you take any data, friends, whatever random data you take, and try and apply this formula and see the resultant value that you are going to get will always fall between 0 to 1. It will always be 0 to 1, no other value. I mean, it cannot go beyond 0, below 0 or beyond 1. Okay, so that's basically the normalization function. And remember, normalization function is making the data unitless. It's making the data unitless. X minus X minimum, right? By X max minus X min. So assume you have a data which is basically talking about salaries or any other data. So if I have to talk about this data, the units either would be dollars or INR. Let's assume dollars. So I'm saying dollar minus dollar this X basically is giving me a dollar minus dollar divided by again dollar minus dollar. So what is happening? This data is becoming unitless. That's another advantage that we have with this particular calculation, normalization calculation. So we apply that normalization to the data to bring the scale of all the data points now between 0 to 1. Next, I'm converting this data into an array format. Array is nothing but a multi-dimensional vector, right? So here I'm converting that into two parts. The entire data is getting split into two parts: input array and output array. Output array is, of course, it's a univariate data. You'll have only the outcome, the final outcome, target variable. But whereas the rest of the input variables have to be used, right? So I'm saying X equal to n array on the normalized data, the two refine normalized data, right? WBCD underscore n. On that data, we define again to the location. So first, normalize the data, right? Then cross-verify, then measure, then do the split of input-output. So this is input variables and this is output, right? And convert that into array format. Now, once I do that, we need to partition the data set. And partitioning can be done in any proportions. The test size obviously should be less than the training size. And here in this example, I'm using 33% as the partition value. That means you are going to split your data into 67 versus 37. Right? So that's basically how we are splitting the data. You can change this number to anything you wish. Yeah, it's not defined. That's because I have not executed the line number 24. So let me first import this inbuilt function and then split. Again, X is not defined. That means I have not executed this. Okay, let me execute this. Then I'll say split. So now what happened, if you see here on the right side, you get X train X test, Y train Y test. Right? So the variables are partitioned now. Now on this partitioned data, we have to apply K nearest neighbor, K neighbors classifier. So we import that library called neighbors, and from that we are importing a function called K neighbors classifier. And I'm defining what it needs to do. So when the code is passed with the data, it will have to consider 21 errors. Yeah. So I've defined my KNN algorithm. Again, I have not imported this. So once you import the library, you should be able to use it immediately. And then we are fitting the training data. Right? We fit train data here. Right. When I fit this train data, the model gets identifying, or the model identifies the rules that we have generated. Right? So it simply passes the data into the equation and generates the results, or generate the equation. Now from that equation, I will have to predict. Right? I have to predict the value. And in order to predict, we try and use cross table. Right? And passing the actual data and predicted value. And when we do it, again, predict is not defined. What did I not predict? Okay, I did not predict this. So let me predict this. I've fitted, I've predicted, and to measure the accuracy, how well this model has predicted, we are using this cross table function. Now, cross table is a function which basically is trying to estimate the accuracy of your model. Your model is said to be accurate if that model is correctly predicting. If it is correctly predicting benign cases as benign cases, malignant cases as malignant cases, right? It has to predict that way. And we can see here on the screen, this one. We are passing the actual data and predicted data. So the actual data is on here, rows, benign and malignant, and these are the predicted values. So that means out of my total number of observations, which is test data, 188 observations, the model has correctly predicted benign as benign in 117 cases, correct predictions. Similarly, the model is able to identify the malignant cases as malignant, 60 values out of 69, 60 values are correctly predicted. Now, if I want to get the accuracy of the model, we have to add these two, 117 plus 60 by the total number of observations, which is 188. This is 188, right? So that gives us the accuracy. We can also use this inbuilt function called accuracy score to deal with the same calculation. It will give you the same result. 94%. So the model that we have developed here is 94% accurate. That means if you are asking this model, the KNN model, to predict, let's say on the new patients, whether they have cancer or not, benign and malignant, then the model is able to predict 94 people, for 94 people. Out of 100, it is able to predict correctly for 94% of the people. But is this the right prediction? It may not be just by a fluke or just by a chance, right? So we will also see how well it is getting actually trained. So I will take that training data. You can see this training data, right? and we cross verify on what is the prediction on training data. Okay, this is still test data. This is another way to measure accuracy. Same result, okay? It's just another way. And we are applying the same thing for training data. So you predict by passing training data and see what is the accuracy. And that accuracy is this. Now you can see that the KNN model that we have developed, right? Using how many Ks? That K is explained here. So if I have data scattered like this is your training data. How many training data points are there? 516. I take 188 test data, I'll take the first value and plot it wherever it falls, right? And plot it. Measure 21 shortest distances. And based on the majority, we classify whether that new record should belong to the benign class or malignant class. Is this clear, friends? Is this logic clear? Are you able to understand this logic? Yeah? All right, so we'll take a break now. Right, it's 3:22 now. We'll connect back at 3:30. Okay, 3:23 now. We'll just connect back in 3:30, and then we'll talk about something very interesting called as decision trees. It is widely used in financial sector, and of course, it is used in various other sectors as well. But broad applications are developed in finance sectors, right? So we will look into that. Yes, Jalinder, it is using 21 short distances and it is a random number. We keep trying with different K values and measure the accuracies. Okay, we'll discuss that post the break. In the meantime, you can post all your questions, friends. Keep posting your questions. We'll discuss on the questions post the break. Hey all, let me take up your questions now. Hope everyone is back. Okay, no questions? Wonderful. All right. Yeah, please post your questions, friends, if you have any. So as part of the discussion till now, right, we basically studied about ML techniques in which we are looking at predefined equations, predefined techniques. And in this predefined techniques, we looked at regression, interpretable models, right? Regression. And then we also looked at the KNN classification technique. Now we also have another technique, which is classification rules-based technique. Classification rules-based technique. So this classification rules-based technique is generating rules to classify the data. And we call this model as decision tree. Decision tree is basically a tree-like structure, tree-like diagram that we get, in which we have these three nodes, right? It starts with root node, and then we'll branch out the data by asking certain questions. And we'll try to branch out till we end up getting the final output, right? Like this. So decision tree is a tree-like structure. This is a tree-like structure in which the internal nodes are representing a test on an attribute. Attribute is nothing but your variable, factor, or you can also call it as a feature, right? And each branch represents the outcome of that test that you're conducting. And we repeat this till we end up getting leaf nodes. And it is called as a rules-based technique because this tree-like diagram that we are generating is giving us rules to decide on output. So a path from root to leaf is basically a classification rule, one rule, right? So let us look into an example here. This is how your tree looks like. This is your root node. Every tree that we are starting to develop will start at root, and we will have these internal branch nodes or internal nodes. And then finally, you will have these leaf nodes. They are also known as terminal nodes. So what we do basically here is, look at this. You have to take a decision. Okay. The name of the algorithm is called as decision trees. So we'll have to take a decision. Now that decision here is your output variable, which basically saying, would you allow a kid to play or do not allow them to play? Not to play. Do not allow them. Okay. So if I have 14 kids previously, my historical data, we have 14 kids. And out of those 14 kids, we have allowed 9 kids to play, 5 kids not to play. But what we are basically doing here is taking that historical data and looking at on what conditions we allowed them to play and what conditions we did not allow them to play. So we first verified what is the outlook like, right? The climatic conditions outlook. There are 3 different conditions: very sunny, cloudy, and rainy. right? So we have three different categories or outcomes. Now, when it is sunny, right, you might want to further check on what is the temperature. If the temperature is less than or equal to 30 degrees, then you are allowing them to play. There's no harm. So kids can play outside if it is less than 30 degrees. But if it is greater than 30 degrees, then you're deciding them not to play. It's very, very hot outside, so do not play. Then we have cloudy condition. In cloudy condition, there is no harm at all, right? So you allow all the kids that are there here to play. So you have 5 kids, 5 scenarios coming under this category, 4 scenarios coming under this category, 5 scenarios coming under this category. Now, under the rainy conditions, you have 5 scenarios. I mean, 5 kids falling under this case. And you're looking at windy conditions. It is raining fine, but is it too windy? If it is too windy, then do not allow the kids to play. But if it is normal, it's not windy, then probably you are allowing them to play soccer. Soccer is best enjoyed in the rain, right? So we allow the kids to play here, right? So we are creating this tree-like diagram and generating rules. The first rule that we are writing for ourselves saying that, hey, if the outlook is sunny and if the temperature is less than or equal to 30 degrees, then allow them to play, right? If the outlook is sunny but greater than 30 degrees, then do not allow the kids to play. So that is one rule, 2 rules. So we have 2 rules generated here. Similarly, I'm generating 1 rule here. We are saying if the conditions are cloudy, then no problem, allow them to play, right? So this is how we write rules. Each path from root node to leaf node is considered to be one rule. Now, decision tree is all about generating those rules. And these are the conditions that we need to look at. The algorithm is a very simple, basic algorithm. And we call this algorithm as a greedy approach algorithm. We are greedy for the information. That means if you take a business scenario and you framed your rules using decision tree on the historical data, we have framed rules. Okay? Now, in these rules, I mean, if you have too many rules, would your customer enjoy answering those questions? Would you be able to take a decision quickly? No, right? It will take time for you to come to a conclusion. But if you have less rules, you will be able to take the decision that much quicker. And your customers would also not feel discomfort. So we need to develop a tree which can give us the least number of rules, less number of rules, right? Yeah. So that's the logic. We are trying to become more greedy for the information. Okay? But what is the logic? What we actually do, on what basis we need to split the tree and grow the tree, is depending on a statistical measure. We use this statistical measure. We count the value of each split. And that formula is called as information gained. Information gain. So let us go to that point. Okay, so this is the data set. Assume you are working for, you're basically helping a organization which is into selling the computers, okay, computer accessory store, an electronic store or electronic gadget store, and people are visiting the store to purchase these computers. So we have 14 records here. We have age, income, student, and credit rating. Given these input factors, right, we have to try and predict whether the computer will be purchased by the customer or not purchased by the customer, right? So we will take student as the first logic, first node. And we are asking, as soon as a customer is walking in, we are asking him, and hey, are you a student? Now, if he says yes, then put him into this data set. If he says no, put him into this. Right? That 14 records that we have, using that we are defining these conditions. Next, here probably I'll ask income. Right? You can choose anyone. Let's say I'm choosing income. Here also I'll choose income. Then further my data is getting split. Right? So like this, we keep splitting the data till we are end up getting a decision. I should be able to finally take the decision. And then using this decision tree that we have generated, we create the rules. If the customer is not a student and if his income is high, but if his age is less than or equal to 30, then he is not going to purchase the computer. But if his age is falling between 31 to 40, then he is going to purchase the computer. But if this customer income is medium, then we have to look at credit rating score. And if it is excellent, then we come here and we again verify his age. If his age is 31 to 40, he is purchasing the computer. But if it is less greater than 40, then he is not going to purchase the computer. Whereas if the credit rating condition is fair, again you will have yes and no cases. So similarly, we look into all the branches and we generate these rules. Right? We are generating the classification rules. We generated 11 rules when we started the development of the tree with student. Similarly, I can experiment on creating another tree on the same historical data using income now. So we keep generating like this and we get this tree. And on this tree, we get 10 rules. That means one rule less. Right? We get one rule less. So comparing both the trees that we have generated, the second tree would be better because we have one tree less. So one rule less, right? So we have to identify what is that tree. Let me show you. What is that tree which gives us the least number of rules? So if you observe here, I have only 1, 2, 3, 4, 5. 5 rules are being generated when I started with age and used student and credit rating in between. Right? So we need to develop this. And in order to develop this shortest possible tree will be done using a concept called as entropy. We use entropy, which is also known as information theory. We have to calculate the information gain. Right? This information gain is trying to identify how much information can we extract. How much information can we extract when we are splitting a tree, when we are splitting the entire data on a specific attribute X. Yep. So if I use this formula, the formula is minus summation of P of I log base to P of I. Now in our data set, the output variable is Y, I mean computer purchasing or not purchasing. It is a 2 categorical value. It's 2 level, right? We have 2 values. So we are going to extend this formula that we have just written, right? Minus P of summation of P of I log base to P of I. We first have to calculate the entropy. Remember, entropy is nothing but the information that we can extract from the variable. So you might get confused on, hey, what is all this? What is entropy? What is information that you're talking about? Just to give you an example here, let's say I'm conducting a quiz, guys, okay? A surprise test, like what you do, right? So I'm conducting a surprise exam here. Out of, let's say, 10 questions. And when I look into all these answers, when you have written all the answers, when I look at your answers, I find that everybody is getting 8 out of 10. Everybody is getting 8 out of 10. Right? Now, if this is the case, then will I be able to distinguish among you all people? Would I be able to tell who is prepared, who is not prepared, who is just listening and forgetting the things this FDP program is conducted for free for you all, right? So how many of you are actually taking advantage of this? Or how many of you are just attending for the sake of it? I will not be able to tell all those details if I get same marks for everyone. But if I can get, right, when I'm conducting this exam, if I am getting marks like 2 out of 10, 5 out of 10, 8 out of 10, 10 out of 10, if I see this variation, right, then I would be able to explain a lot of things about you people, isn't it? I will be able to talk about a lot of things about you people by looking at the marks. So if I have variation here, I need to capture that information. I need to capture that variation, right? So if you see here, I have S, no, S, no, so is the variation, right? The output variable is either S or no. So I will say minus summation of P of I log base to P of I is trying to capture that information or entropy or variation. So minus, how many yes are there we have to see, right? Minus summation of P of yes, probability of yes cases, log base to P of yes, minus P of no, log base to P of no. That's the equation. And if you calculate probability, you will get the value substituted into this and you'll be able to get the result. Similarly, we have another formula which basically is talking about the information that we can extract from the input variables. This is with respect to y, and this is with respect to x if you are splitting that y. So before the split, after the split. entropy after the split. And here we are calculating again entropy, adding that value with all the splits. For each split, what is the entropy is what we calculate here. So let me show you that. So customers purchasing, we have 9 by 14 probability. Not purchasing, we have 5 by 14. So this is the probability. And when we do the calculation, applying that values into the formula, we get 0.94. Now assume that we are using age as the first root node to make the partitions. Now in root, in this particular, age, we have 3 categories. Less than or equal to 30, 31 to 40, and greater than 40. So we are breaking that into 3 different groups, right? Now in each group, how much entropy is there is what we need to calculate. Again, remember, entropy means variation. If you don't have variation, if you see here, for less than or equal to 30 data set, we have 5 values which are falling under that category. And there is a variation here. 2 of them are purchasing, 3 of them are not purchasing. But if you look at 31 to 40, there is no variation at all. All the values are purchasing only. All the customers are purchasing. So because there is no variation, the entropy that you're going to get is 0. You will be able to take a decision if you know there is no variation in the data. Homogeneous group is what you're creating. Again, in greater than 40, you again have variation. More the variation, more the value, right? And we substitute those values into the equation. And when we do that, we get information needed. So we have information needed, information expected. Entropy, and this is the entropy post the partition, post the split. And we do a difference here between before the partition with after the partition. And we get this result, right? If I am partitioning the data using age, then how much information am I able to gain? More the information I'm able to gain, better the partition. So we will have to calculate this value for all the attributes, right? All the attributes. And among all these attributes, age is giving us the maximum entropy, information gain. So we use age as the root node for partitioning, right? And we split it like these 3 values. And then again, we treat this as a data set. We partition it further by applying the information gain theory. This is another data set now. Again, you partition it using information gain theory. And here you can see that all the 4 customers who belong to this group of 31 to 40, they are purchasing the computers. So when a customer is walking into the store, I would ask him one question, hey, what is your age, sir? And if he says his age is falling between 31 to 40 years, then I know for sure that he's going to purchase the computer. So I can basically spend some time with that particular customer because he is doing business with me. I know that he's going to spend money and do business with me. So I can appoint a salesperson. I can treat that customer in the most appropriate way, right? And share a lot of information and make sure he is, right, satisfied with the service that we are providing. Customer satisfaction basically is something that we need to take care. So that's the application here. And when we split it further, these are the 5 rules that we are getting generated. These are the 5 rules. So this is decision trees, which is basically called as greedy algorithm. We are applying greedy algorithm, wherein we are trying to extract information gained. You're trying to get the information gained, right? Calculation to decide on the most homogeneous partitions. I have to split the data to create the most homogeneous partitions. Yeah, so that's the classification rules based concept of decision tree. So there are various other ways to generate the machine learning algorithms. This is one of the ways. So you can see here we are doing predictive modeling. We are under shallow machine learning models. We have KNN. This is what we have discussed. It is also known as memory-based reasoning, right? Lazy learning, example-based reasoning, instance-based learning, case-based reasoning. So these are different names which are given for KNN. And we have also discussed about decision tree now, greedy algorithm. So these are falling under your predictive modeling. Predictive modeling. Now we will learn about the most happening algorithm tomorrow, which is neural network. We'll talk about neural network, friends. That would be our next topic. So what is perceptron algorithm? How the neural network actually trains. It trains a machine to find the most appropriate equation, right? So all those things we will try and understand tomorrow. Let me take up your questions in the meantime. Probably you have the attendance link. Okay. So I see a lot of people are, rather than focusing on what I'm saying, you're more concerned about the attendance, is it? Okay. Any questions on the topics that we discussed, friends? No questions at all? Okay, once again, please make sure you're using this mind map. You can share it across to your associates, close associates as well. It will serve as a very good reference for people who are trying to learn the data science concepts, which will also include machine learning. And if you wish to go through few of the concepts again, then you can always refer to this YouTube channel, friends. I've already shared this, but let me reshare it again. So you can refer to this YouTube link and yeah, take the advantage of the sessions which are already conducted here, right? So many videos are there. You can take up those videos. Any questions, anyone? All right. So I'm assuming no questions, friends. Okay. I think we have a question here. What is meant by weighted KNN? Weighted KNN basically is an application where you give more weightage to a specific variable. You pass on a parameter specifically to give more importance to that parameter when you are trying to train your algorithm. It's one of the approaches that we take in KNN. What we discussed is very simple vanilla model of KNN, simple distance-based method. Greedy algorithm application, well, it is used in banks, Soundarya. Predominantly, it is used in banks to identify whether a customer would be, let's say, a defaulter or not. So, for example, you're applying for a bank loan, right? Bank is collecting entire information about you. They create a profile, and then they pass this details to a decision tree based algorithm, which has rules created, right? And in that rules based algorithm, it will try to identify what all those factors which are influencing you to become a defaulter. It tries to map those things. And ultimately, it figures out whether you will be a defaulter or a good customer to the bank, upfront predicting it. And based on that model, we will the bank basically approves or rejects your loan application. Now, that's one of the application that we can talk about the decision tree. Divide and conquer, the greedy approach. Yes, that's correct, Amuta. Divide and conquer is nothing but you are splitting the data set, right? In order to extract the information, we are splitting it so that we get most homogeneous pairs. So both are same, yes, decision tree. Feedback link is there all in the same link, Ravichandra. The attendance link that you have, right? Within that, you will have feedback link as well. Okay, I've calculated minimum distance of classification question. It gave me minimum distance as 5 for 2 categories, protein and fruits. Then what to do? You change the K value and check. So what is the K value that you are taking, Anshu, is a question. If you're taking a K value as even number, then there might be this ambiguity, right? You change the K value and check. If you take K equal to 1, you might get one value. Let's say 5 is the least distance. In that case, you are getting one protein, the other one is fruit. If you change K equal to 2, you will get additional information on top of that, right? Or K equal to 3, and then see. Majority is what we have to look at, Anshu. Got it? And generally, when we are developing a KNN algorithm, right? We look at what is the output variable category. How many categories do we have? In our example, it was a 3-class problem. It's a 3-class problem, right? So we had fruit, we had protein, and we had vegetable. So make sure you do not take the K value, which is multiples of 3. That would be basically I would say it would generate an ambiguity case, right? So to make sure we have majority, we always have the K value, which is not a multiples of 3 in this case. And we keep changing the K value. Always go with majority. If you're not clear on majority, then go with the shortest case. Swagota, we have already shared, right? The Anaconda software. Have you not installed it? Yeah, this is the software download link. You would have to install Anaconda software and get the software. And that gives us various options. And one of the option I am preferring is KNN method, sorry, Spider. You can see here, Spider application is what is I've been used. Right? Any further questions? Yeah. Yeah, friends, please ask your questions. Hope everyone has given your attendance. All right, friends, so let's wrap up. If you have no questions, we'll connect tomorrow. And tomorrow we are going to discuss about the black box neural network techniques. Okay, very interesting. It depends on how our brain actually is learning things. On the same logic, neural networks are developed. So let's see you guys tomorrow. Until then, take care and be safe. Thank you and good evening, friends.